Okay, then I'm going to share my iPad. It's already shared. iPad is already shared, right? Okay, so I'm going to talk about another tool. Center manifold is one case where we look at the non-hyperbolic fixed point. Another tool is the so-called normal form. So I will talk about the normal forms. So let me go back to make an example. So we have talked about this bifurcation. One of the most simple bifurcation that we talk about was this case, the one-dimensional dynamical system. So certain parameter plus x squared. Okay. So the linear term is missing. If there's a linear term, then it's hyperbolic system. But if the linear term is missing, then there's a bifurcation at r equals 0. What kind of bifurcation? So when r equals negative, you have this kind of picture, right? That's the, I'm trying to draw the graph of x dots so that to find out the phase portrait. This was what we did a long time ago. So when r is negative, we have such graph, which means that this point where x dot is 0, so those are fixed points. This is unstable fixed point because here you get, and the left one is the fixed stable fixed point. So this is stable, unstable. And if r is getting increasing, getting smaller to 0, then what happens? These two fixed points getting closer. When r equals 0, they merge. And when r is positive, so as r moves, this graph goes up. And when r is positive, the fixed point disappears. So in the bifurcation diagram is the x-axis becomes parameter, while the y-axis is the space where the dynamics occurs. So you get two fixed points. One is the unstable, here is unstable, and here is the stable fixed points. And then they merge and then disappears. That's bifurcation, and this bifurcation is, I think that is called saddle bifurcation. Stable and unstable. Okay, so of course, saddle bifurcation happens not only for this particular equation, but in many different equations. But this is one of the most prototypical type of bifurcation, and we call this thing a normal form. Normal form for saddle bifurcation, the normal form. That's the normal form for the saddle bifurcation, meaning that any saddle bifurcation can be understood in this form. So what do I mean by that? So if I have any other complicated graph of x dot, and then saddle bifurcation happens whenever you have such local minima touching the x-axis. Whenever such local minima touching the x-axis, and then if there's a certain parameter that moves this graph up and down, so if there's some parameter such that when the parameters, so this is happening when some critical value, and if this thing happens when this is less than critical value, and another case is happening when it's bigger than critical value. If there's such situation, then you will have exactly the saddle bifurcation locally around that point, right? So you have stable fixed point here, like unstable fixed point and stable fixed point. The pair of stable fixed point and unstable fixed point will merge as R grows to R critical and disappears as R is bigger than R critical. Whenever such thing happens, you get similar saddle point bifurcation. And there let's write down. So x dot is a function of x, and also it's a function of this parameter. And you can Taylor expand the right-hand side. So what's the general Taylor? So Taylor expansion around this point x star and RC. So that's the point where you Taylor expand. So the first term will be this. And then the linear term will come, x minus x star times the x derivative of f evaluated at this point, at the point, star RC. And the linear term in R minus RC, and also partial derivative in R of x star RC, and so on, right? Let's write down also the quadratic term in x, the 1/2 for the Taylor series in x square, and the second derivative in x, and go on, and keep going, higher order terms. So those are Taylor expansion. And you can see from the graph, this thing goes to 0. The first term is 0, because f, the value of x dot is 0, x star and R equal RC, right? And another thing that's 0 is this one. That's also 0. Why? Because here, at x star, the slope is 0, it's horizontal. Slope is 0 when, for this case, at x star, the slope is 0. So this is also, the first two terms 0. So the surviving term, among the surviving term, the smallest terms are these two. And my pen just died. I need 1 minute break. Okay. Yeah, and let's measure 1 minute. Yeah, let me do some advertisement while this 1 minute. Advertisement of the Dynamical System 2. Dynamical System 2, appealing thing is no homework, no exam. Just chat with me. That's the requirement. So occasional communication with me. So class participation, only with class participation. And Dynamical System 2, until last year, was taught by Professor Yu. So he did some PDE courses on Dynamical System 2. But I changed the subject. So this time, so if you go to the department website, they still describe this, the previous dynamical system too. Okay, 1 minute passed, but I will keep going with this advertisement. But this time I will cover the complex dynamics. So the basic goal is just to describe introduction to the complex dynamics, which is the study of the Julia sets and Mandelbrot sets. So when you see this picture, where this picture come from, what's the property of this picture? All this picture is coming from just simple function, quadratic polynomial. But it has so richness in this just simple quadratic polynomial. And we, of course, the theory that we learn is not just true for quadratic polynomial for other, but for other case too. But quadratic polynomial is just illustration. The property that we get from quadratic polynomial is universal. But that's the basic plan. We want to study those pictures. The property of Julia sets looks crazy, so we will see what's crazy about those pictures. And no textbook, because yeah, I'm going to follow, I think mainly the textbook by Milnor. Milnor's textbook, there are several more textbooks on complex dynamics, Gamlin, Milnor, but Milnor's textbook is always the most easy to, most perfect to read in every subject. Yeah, did I say no homework, no exam? Okay. Yeah, so that's dynamical system 2. It's separate from this course, but this Julia sets and Mandelbrot sets is happening in the complex plane. So I think you need to have some background in the complex analysis, like at least the undergraduate level complex analysis. And this piggyback courses and the real analysis that you first learn about epsilon delta stuff. I think that's enough to follow this course. Okay, any question about this course advertisement? I think I will send the email, also group email soon. Okay, so let's go back. And from the leading term, you will see that if we make a new substitution of the new coordinates, something like that, and another coordinate, something like that, then x dot bar, x tilde dot, x tilde dot, which is same as x dot, is given by r tilde and some coefficient here. That's a number, right? That's number because it's evaluated at x star and r is critical, RC. Plus certain other number times x tilde square from this term. So this term is coming from here. The second term is coming from here. Again, some number because this first some number. And the higher order. So you see this normal form. So whenever you have saddle node bifurcation, saddle node bifurcation, saddle node. I forgot the name. I think saddle node bifurcation. I think there was also a name like blue sky bifurcation, which refers to the same thing. Because if you run this bifurcation backwards, then there's nothing, and out of blue you create one stable and unstable fixed points. And so this creation of two fixed points out of nowhere, so that's the name blue sky bifurcation. Anyway, so we get the normal forms as a dominant term in the Taylor series. So the question is for a more complicated case, multidimensional case, if it's not hyperbolic system, then the second order terms in the Taylor series important, the next order term. So in the hyperbolic case, hyperbolic fixed point, the first term, the linear part, it completely qualitatively determine the dynamical system, right? Near the fixed point. Because you can linearize, and the eigenvalues all completely determines. But if it's non-hyperbolic, then the linearized part is not enough, and we have to consider the second order, the quadratic terms and higher order terms. And if you look at the quadratic terms, say it's a two-dimensional dynamics, then the quadratic term has x squared. So if it is two-dimensional dynamics in terms of x and y, then what's the all possible quadratic terms? X squared, xy, and y squared. And that can come in the x dot, the speed of x, or also in the y dot. So there's three possible quadratic terms that can come into the x dot, or three terms in the y dot. So there's 6 total different possibilities these quadratic terms can affect the dynamical system. Is this all giving you different possibility, or some of them are qualitatively same, like in this case. So even though like in this case, what case? No. So even though there are 6 possible quadratic terms that you can add to this two-dimensional dynamical system, when it's not hyperbolic system, they are not all qualitatively different. Some of them are equivalent or under change of variables, and we want to count exactly what's the qualitatively different quadratic term next to the higher terms. And that's answer is given by the normal form. Normal form, up to change of variable, it describes.
I found this on the web for answers given by the normal for normal form. Check it out.
Yeah, I'm not lonely because of the Siri. Okay, so that's the normal form. So non-hyperbolic case, what's the how to understand the next order higher terms? What's the significant next order terms? Count all the possibilities. That's the normal form. So let's consider general case in n-dimensional dynamical system. And U is n-dimensional dynamical system. So U of t is in RT, and A is in matrix n by n matrix, n by n matrix. So linearized term, I pick a linear term separately as A times U, and f of U is of course again n-dimensional vector. Is it clear? So f of U will contain higher order than linear terms. F of U will start from quadratic terms. Around the fixed point, maybe we have to yeah, let's assume assume all through this discussion that zero vector is the fixed point. And zero vector is, if it is non-hyperbolic fixed point, what's the non-trivial expression that matters for f of u? Oh, come on. Okay, so that's what we want to do. Okay, so let's consider. Let's consider diagonal case. So lambda is diagonalized. So when A, the matrix A is diagonalizable, it can be in Jordan form in general, but assume first the diagonal case. Then by transform of U, so certain linear transform of U, you can make into this form. So let's consider this form. And the first, consider first is this case, n equal 2. So lambda is lambda 1, lambda 2. And f of u is therefore, let's write f of u as also f of xy. It's two vectors, this one and this one. And we are expanding around the fixed point, the origin. And f is from the second, is starting from the quadratic term because the linear term is already taken care of by this lambda u part. Okay, so let's say lambda u. What is u? U is equal to xy, two dimension, n equal to. Okay, and here what do we have? F1 can have, let's say, this term, xy term, and y squared term, and the higher order terms. Now, let me use higher order term to be HOT. F2 also similarly B1 of x2, B2 of xy, B3 of y is 3. So higher order term, when lambda 1 and lambda 2 are not exactly in hyperbolic case, then the higher order term matters. So there's three, as I said, 6 possible degrees of freedom in where the higher order term can matter. But there's a freedom of change of variable, and according to the change of variable, not all these six possibilities are different. And we want to classify what's the qualitatively different way, the space of parameters among these 6 parameters that can result in a different, qualitatively different dynamical system near the origin. Okay, so okay, what we do is up to change of variable. So we will do the change of variable. So you will change u into u plus h of u. I will do the change of variable and more explicitly. I will change the variable into plus h. Okay, h1 and h2. h1 of x, h2 of h1 of xy, h2 of xy. So this is a certain change of variable. So we are defining sort of new coordinate x mu and y mu from the old coordinate. And we will rewrite this equation in terms of the new coordinate. And this freedom in choosing h1 and h2, which is similar as starting from the quadratic terms, can we absorb any of these parameter, 6 parameters by this new, by this freedom of h1 and h2? That's what we are, we wonder. So let's rewrite it. So x mu, y mu, it's given by x and y plus, okay, how can I write? No, just a second. I think I have used the notation wrong. No, that's fine. Okay, so I will Taylor expand H1. Taylor expand H1. So you have x times H1 evaluated as 0 is 0, 0. And y times H1 evaluated as 0 and 0. And the high order. The same thing below, x times Taylor expansion as 0 origin, y times h2, and the high order. Okay, so I can rewrite this one as the following: xy plus let's right. There's yeah, this is stupid. So linear term is already. So what's wrong with this? So this is all 0. This is all 0 because the linear part, that's the linear part. No. So we are defining a new variable by adding high order terms. So the linear part is already taken care of by the first term. So we need further. Just a second. Oh, no. Sorry, so just a second. Okay, I think. Uh, okay, sorry. So let me. No, this part is fine. So for okay, so what we want to do is we are taking the time derivative of this one, then it's taking the time derivative of the right hand side. So taking the time derivative of the right hand side, and then okay, let me rewrite this part. So this this part will be the time derivative of h1 of xy and time derivative of h2 of x and y. Right? And this will be this now can be written as Jacobian here, x derivative in h1, y derivative in h1, x derivative in h2, y derivative in h2 times time derivative in this. So that's exact. So now I can rewrite it as identity plus Jacobian matrix that depends on h. And here, this Jacobian matrix depends on x and y. And x dot y. Yeah. We assume h1, h2, they are quadratic in Taylor series expansion. So this Jacobian will start from linear term. So they will be O of x and y. Since h is the quadratic in x and y. So single derivative of that is big O of x and y. Okay. So using this new x and y, let's rewrite this original equation. So du dt will be du mu dt minus, no, y dt will be actually 1 plus Jacobian h x y inverse of du mu dt. Did I? Oh no, the opposite. Oh no, right, correct.
Yeah, that's
Yeah.
right.
Why does it look so strange? Okay, so that's the left-hand side. Now I want to change the right-hand side. Lambda mu plus fu u relation with the so this becomes u nu minus h of u. Right.
HU.
H of u is this one. This part is u nu. I
Oh,
define u nu as u plus h of u, where h is some quadratic correction, quadratic and higher term correction.
I see.
Okay. This one, point one.
Don't we need to change the FU? This U is
If fu is here, yeah, we have to change fu also. So everywhere we want to change u to u nu.
yeah.
Yeah, yes, right. And okay. So this thing is u nu minus h of u. So h is quadratic in x and y. So if I change u into u nu, then there is a difference of order cubic difference. So the difference will be big O cubic. Okay. So u and u nu have this relation. So u nu is u plus h of u, and therefore, what is this meaning? So this means u plus this part is right, and therefore, therefore you also get the up. Why? Why is this? So, yeah, yes. Okay, so what this means?
Just square both sides, right?
Square both sides. Oh yes, square both sides.
OU cubic.
Right. So something. Yeah, U is a vector, but
It doesn't matter, right? I mean, take the modular.
something like that.
Yeah.
Right. So what was I going to say?
So OU square equal to OU nu square.
Right. So what I want to say is this this is this.
And this is from the original one, it's true.
What? I mean this.
Yes.
So, so yeah, what I think it's so if U nu is Taylor expand like this, then inverse Taylor, so U will be Taylor expand also in terms of U nu, right? So
Yeah.
if there's
Yeah.
a Taylor expansion starting from, then the inverse Taylor expansion will be, so if some function is Taylor expanding, yeah, U plus C1 U squared plus and so on, then the inverse function. Inverse function will be also Taylor expand. I think it's probably this.
Is it? That's the receptacle of the F, right? Not.
Yeah, let's maybe true. Let's see.
I don't know. It's not like a matrix. For matrix,
Yeah, it doesn't sound right. So let's check. So this thing, so let's say this is tilde and find the tilde. So this means f of u minus c1 tilde f of u squared. And f of u, let me just keep the first two terms. And for the next term, let me just keep the first term, which is this, and the higher terms, right? Yeah, C1 and C1 tilde has to be the same. So I was
okay.
amazingly right. So C1.
Oh, I see. Yeah.
Okay, so given a Taylor series like this one, then it can be inverted also. So which means that if I change U by U nu, then the U will be exactly U nu plus high order. And H is already quadratic. H is, starting from u, big O of u squared, or big O of the argument squared. Okay. H is already quadratic, therefore the error here will be high order. Is it okay? So H of u is already high order, and therefore H of u nu plus something big O squared will be
OU nu cubic. No.
It will be H of u nu plus
Yeah, OU nu cubic. Now
right,
it's cubic too.
plus something high order. Okay. So I can change up to the high order. And the same thing here also, because f is also quadratic or higher. So I can change u to u nu with the same up to high order. So the right hand side just changes. Okay. Now let's combine the left hand side and the right. So again, the left hand side also, you can change this x nu y nu. You can change this x and y into x nu and y nu. Yeah. Nu. And then by this change, there's some correction, and the correction is plus O of u squared. So up to squared, you can change. Okay, so I think I changed the left-hand side and the right-hand side. Okay, so now let's combine. So this is the left-hand side, or this is the left-hand side, and the right-hand side is this one. 1 plus JH inverse. Now let's move on to the next page. Identity plus JH of x nu y nu. But now let's change all the x nu and y nu into x and y, because now I don't need this x nu. I don't need the original x and y, so I will just looking at the new coordinate. So let's so plus big O of u squared. So that's again u nu, also rewrite it as u. This inverse times x dot y dot. Is this the left hand side? Yes, that's the left hand side. Is equal to the right hand side lambda u h u f u. Lambda u h u f u.
So what is OU square?
This part is the correction. So I have still the correction.
Yeah.
This OU squared is coming from here?
It's a matrix.
Oh, yeah, yes, matrix where each entry
Has
uh,
second order.
quadratic or higher.
Okay, okay.
Okay, so now we can rewrite x dot y dot equals identity plus jh xy times lambda u minus lambda h of u minus f of u higher. So let's collect order by order. So the largest order in the first factor is identity. This is the dominant order. So the first term is lambda u. Let's use x and y. So that's obviously the linearized part. Linear part doesn't change because our correction is all sublinear. Okay, now so this is the linear part. So quadratic part. Quadratic part is coming from this term, and this term, this term. That's all quadratic. Also, this times this is also quadratic because both linear. Right? So there's total 3 terms. jh xy times lambda times xy. So that's 1 term. And then minus lambda h of u minus f of u. So there are 3 terms. That's quadratic terms. Okay, and the higher term of the higher term. Yeah, at this point, let me check whether the calculation is correct. Here. Where is the I think so. Okay. So we have used h. Yeah, let me rewrite this part explicitly in component form. JH is a matrix. What kind of matrix it is? It's linear matrix. So it has linear matrix. So okay, so let me write h of u as h1 of x and y, h2 of x and y, and h1 of x and y and h2 of x and y can be also how you can explicitly write this thing. Okay. And what is JH of x and y? The definition of that one, it was all right. Partial derivative of h1, partial derivative of h1, partial derivative of h2, partial derivative of h2. That was the definition. Why didn't I just? Yeah. Okay, so using that, again, so let me rewrite this star. Star is above thing. times lambda 1, lambda 2 times x and y minus lambda 1, lambda 2 times h. H is h1, h2. And in the new coordinate, we want to get whether we can get rid of the quadratic terms by this change of variable. That's what we want to do. So by this change of variable, is there any quadratic term that we can get rid of? When it's hyperbolic system, you can get rid of all the quadratic terms. So hyperbolic system is essentially described by the linear terms. So quadratic terms are not important. So you can get rid of all the quadratic terms. You will see. So what we mean is, we want to make it 0 as much as possible by choosing our h. H is the change of variables. So by choosing h, can we make this term 0? Can we remove by choosing the function h, choosing the change of variable? You were saying something, but it was okay. No, okay.
Yeah, I was saying that then you have to solve a PDE, right?
PDE? No, this is all just linear algebra, because we just want to solve this part.
Because JH is a function, right?
Yeah, JH is function, but we only want up to quadratic order, so everything else is here. So we only want the linear part of JH. We only need the linear part of a. So that's why I want to. So let's say if we have the explicit expression, let's say here, H. I hate to write the explicit thing here. H. This is bad. H11, H12, H13. So these are coefficients. And the high order term.
Oh, I see.
H21, H22, H23.
And the JH only consider the linear term.
And this part also can be expressed. How does it express? H11, 2 times x.
Yes.
And
H12y.
H12 y. That's the linear part. The H1y is.
No, there's more. Oh, no, that's it. Yeah.
Yeah, up to the linear term. That's and 2 times H13y, and so on. So up to square term, right?
Yes.
So JH, of course, has infinite Taylor series, but we only care about removing this term up to the quadratic terms.
Yes.
Okay. And so that's sort of bad notation, because we only the linear term. Okay, so if you look at, so the star is this thing, and we want to make this expression to cancel to 0. So we will look at this part. This part has to cancel f of u. F of u is whatever is given from the dynamical system. And this circled part is what we can change by the change of variable h, right?
Yes.
So this part we will write as some operator that depends on h. With the space of that depends. So what is the H? Space of H. Space of H. Space of H. Yeah, space of H is here. Space H is six-dimensional linear space. Six-dimensional space. Space of H is, let's call it capital H. That's the span of six-dimensional space, which is base this, and also base in the second component. That's the space of all the possible quadratic correction to the linear term. So that's span. And so this is an operator. So you can view this as an operator, L of H, where L is a function from H to H. H is L, of course, gives some quadratic function, right? So the first term is linear times linear, so it's quadratic. Second term is quadratic by itself. So the outcome of this part can be also spanned by this. So if I define the whole thing as L of H, this L is taking H and spits out the space in H, right?
Yes.
So if this mapping is onto, if this mapping is onto H, so if you can produce any H, any element in capital H, then it means we can choose H such that we can cancel F of U, right? But if you cannot, then there's non-trivial leftover that we cannot cover by the image of L, then those non-trivial leftover can be the normal form that we cannot get rid of by the change of variables. So that's what we want. Okay, so let's check what's the individual mapping. So L is the linear, also it's a linear mapping. Therefore, if we know, if we can calculate for all the bases in H, then we can find out the full map. Okay, for the first map, what is L of this one? That's so the first term is the partial derivative in x to 2x, and partial derivative in y is 0 and 0, 0. So that's this first matrix, and y1, lambda 1, lambda 2, x, y, minus lambda 1, lambda 2, and here h is this. So that's the calculation of the first basis element. You know where we come from, right?
Yep.
It's coming from this part. Okay, now if you calculate, then it's very easy to calculate. So it's the 2 lambda 1 x squared 0, the first term, right?
Yep.
And the second term is just
lambda 1
squared 0. So the answer is lambda 1 times x squared 0. So this turns out to be eigenvector. Okay, and then let's calculate the next one, L of x, y, 0. So first taking the partial Jacobian, so taking the derivative in x, you get y. Derivative of y, you get 0. This, lambda 1, lambda 2, xy minus lambda 2, xy 0, right? That's not correct. Yes. Okay, then we get here a little more complicated, right? xy, xy. So you get lambda 1 plus lambda 2, xy 0 for the first one. Right. And then for the second one, you get lambda 1, xy. So what do we get? Lambda 2 times xy, 0. Well, again, this is the lambda, it's an eigenvector. The final thing, y squared 0. This is 0 because the partial derivative in x is 0, partial derivative in y, 2y, 0, 0. Lambda 1, lambda 2. Y squared 0. Okay, so lambda 2 y squared, right? That's the first one calculation. The second part is lambda 1 y squared. So here you get, again, eigenvector with the coefficients becomes 2 lambda 2 minus lambda 1. So we just compute the first components non-zero. If you compute the second component non-zero, we will get this exactly same thing, except the role of lambda 1, lambda 2 changes because by the symmetry. So what we covered is if lambda 1 is not equal to 0, lambda 2 is not equal to 0. So this being non-zero, this being non-zero, and if this being non-zero, which means lambda 1 is not equal to 2 lambda 2, then L of H is H. We can get rid of any quadratic terms. So dynamical system equation, the quadratic term of the Taylor series can be completely canceled by certain change of variables. That's the conclusion. Actually, if you look at by the symmetry, you also need lambda 2 is not equal to lambda 1, which come from the second component. So if these conditions are satisfied, then the L of the space H can generate any vector in the capital H space, which means quadratic terms can be removed from the equation. Quadratic terms in the Taylor series can be removed from the equation by clever choice of H, small h, by clever choice of change of variables. So there's no non-trivial quadratic term that can change the dynamical system qualitatively. Okay, but now if lambda 1 is 0, now these are cases that interesting thing happens. So if lambda 1 is 0, then L of H does not produce every vector. It misses 2 vectors, right? Which vector it misses? Lambda 1 is equal to 0, then it cannot produce this one. X squared 0 is missing because lambda 1 is 0. Therefore, it missing, so it doesn't cover all the h's, but missing this one. And from the similar calculation in the second component, it also misses this one by the symmetry. So this is equal to h. It doesn't cover all the space, but it misses this one. And that means that the original dynamical system, which is du dt, and lambda 1x, lambda 2y, where lambda 1 is 0, so lambda 1 is 0, plus, and there's quadratic terms, so this is 0, and there's a quadratic term which can have some coefficient times x squared, and their quadratic terms. This quadratic term cannot be removed by change of variable. So this is the normal form. This is the normal form. Those quadratic terms matters. Those quadratic terms cannot be removed by change of variable. So we have to. And actually, so this part, if you think about it, then it's just the same thing as what we saw for the saddle node bifurcation. So when the eigenvalues vanish, when the slope is completely 0, it matters, the second order term matters. Whether it turns local minima or local maxima matters. So there's such quadratic terms possible. I just want to write down all this possibility. Yeah, but let me write down next time. So you can write all the other 6 cases or 3 other cases. So when lambda is equal to 2 lambda 2, where both are non-zero. Yeah, actually, these 2 cases covers everything, right? By symmetry, right? Right. This case, yeah, actually, this case is only missing thing is this one. So there, the not normal form will be. Oh, yeah, I can finish. Here, lambda 1 is 2 lambda 2, so it's 2 lambda 2 x, lambda 2 y, and lambda 1 is equal to 2. So this term will become 0, so you can add some non-trivial term here. And the high order term, high order in cubic. So these are normal form that cannot be removed. So non-trivial quadratic terms that can survive. So up to quadratic terms, if we consider these 2 cases, then it's considering the full cases for this special case of lambda 1 and lambda 2.
What if all of them vanishes?
I'm sorry?
What if lambda 1 and lambda 2 all equal to 0?
Both vanishes, then there will be more spaces. 2 more, right?
Yes.
So you will get more in the normal form.
Yeah.
Yeah, that's yeah, like you have, yeah, you get more normal forms if you have more non-hyperbolic direction. More non-hyperbolic direction, then you get contribution from the quadratic terms in more directions. So the space gets larger. Okay, and I want to explain. So this says, I'm saying that this gives qualitatively different dynamical system than this original, just keeping the linear system. Just linear system is qualitatively different from this dynamical system where so quadratic term make a qualitative difference. And I want to show you the dynamical system, but next time. What's the visualization of the dynamical system next time? Okay, so thank you. Let me stop the recording. I don't know how to stop. Stop. So you can leave, of course. Please feel free to. Right? Yes.
Thank you. Have a nice day.
You too. Thank you.
Thank you. Bye.